Hello, this is Math 2270 coming to you from the College of DuPage for summer 2020, and the title of this lecture is More Linear and Nonlinear Models in. I'm going to open with a couple of stories. One thing is, life is a word problem. I worked in industry for a long time, and I never had a boss come and say, "Jim, solve this equation." She said, "Oh, all hell is breaking loose. Go see if you can help the people with the problem they're trying to resolve." One such problem was there was a foundry, and they were had a furnace where they were getting the molten material, and this molten material was transported, and humans were involved transporting it over to an ingot making machine, and the ingot making machine things came out, and this was their product. It turned out the quality used to be good at the very beginning of the company, but suddenly they were having real quality problems over here. To make a long story short, what happened is the people who were taking this hot stuff over to this machine were getting better and better at their job. They were not allowing as much time for this to cool here, and so it wasn't coming out with enough cooling time, and the product did not have the required quality. The solution was not to tell the people to work slower. That never works. But we actually built a wall that they had to lift the stuff over before they put it in there, and that slowed them down just enough. The other story I'm going to tell you is that life is messy. This is what the chalkboard that we had in our office at Bell Labs used to look like. And my office mate at the time, Gaylord Richards, is still the smartest guy I have ever known in my life. I remember how thrilled Gaylord was once when I returned from lunch, and he said, "Gee, look what I did." And there was a problem that came out with an answer that was just like a textbook's answer. It was 2. He was thrilled because that had never happened. I bet that never has happened since either. So life is messy. Life is a word problem. Life is complicated. Okay, back to work then. We've already talked about orthogonal trajectories. The balance of Chapter 3 has sections dealing with linear models and solutions and nonlinear models and solutions. We already talked about one of these. In fact, that carbon dating problem that we did the first day of class was in fact a linear model. We solved it as a separation of variables, but it really was a linear model if you look back at it. I'm going to do a couple of examples of this and one of this, and that's going to finish off Chapter 3. Okay, these are mixing problems that we're going to talk about. We start with the substance that's dissolved in the liquid. Liquid will be entering and leaving a holding tank. The liquid entering the tank may or may not contain more of the substance dissolved in it. Liquid leaving the tank will of course contain substance dissolved in it. If Q of T gives the amount of a substance dissolved in the liquid in the tank at any time t, we want to develop a differential equation that, when solved, will give us an expression for Q of T. Note as well that in many situations that we can think of, air is actually a fluid, and so this is a more general kind of formulation than you might like. The main assumption that we're going to be using here is that the concentration of the substance in the liquid is uniform throughout the tank. This really is not the case, but if we don't make this assumption, the problem becomes extremely difficult and involves partial differential equations, which are not the focus of this course. So the mixing tank looks like this. There's stuff coming in. You can think about it being mixed there, and there's stuff being brought out, and often they talk about salt, and then they call this brine, but those are just technical terms. The main equation that we're going to use to model this situation is shown here. The rate of change of Q of T is the rate at which Q of T enters the tank minus the rate at which Q of T exits the tank. And you see the rate of change of Q of T is going to be dQ dt equals Q prime. This is the rate of change. I really shouldn't have wrote that Q of T there, but this is dQ dt is equal to Q prime of T. So the rate at which Q of T enters the tank is usually the flow rate of the liquid entering times the concentration of the substance in the liquid entering. The rate at which Q of T exits the tank is the flow rate of liquid exiting times the concentration of substance in liquid exiting. So here's a problem that we're going to do. A 1,500 gallon tank initially contains 600 gallons of water with 5 pounds of salt dissolved in it. Water enters the tank at a rate of 9 gallons per hour, and the water entering the tank has a salt concentration of this pounds per gallon. Now notice this is variable over time. If a well-mixed solution leaves the tank at a rate of 6 gallons per hour, how much salt is in the tank when it overflows? You know what to do. And we'll pick this up in 13.1.